In these next two center of mass examples, we're going to look at two-dimensional objects. We're going to look at things where mass is spread out in 2 dimensions and how to look at these. This first one, we have this flat piece of metal. It has a uniform density and it has the shape and dimensions shown. And we're going to find the center of mass, the x and y coordinates of the center of mass of this object. One of the things that we're going to do is we're going to use something that we showed for the rod. If we have something that has a uniform density, the center of mass of the object is right at the center. If this square was 40 centimeters by 40 centimeters, the center of mass of the square would be right at the center, at the 20 centimeter point. Well, we have some pieces missing, but the way that we're going to take that into account is we're going to break this up into individual 10 centimeter by 10 centimeter squares. So we're going to call the mass of each of these 10 centimeter by 10 centimeter boxes M. And so we can see that we have broken this piece up into 3 separate pieces. The first piece is this bottom half of the square. It is made up of 8 of those individual 10 by 10 boxes, and so the center of mass of that piece is right at the center at x equals 20 centimeters and y equals 10 centimeters. So we can treat this as just a single point mass that has a mass of 8m right at that center of that piece. For this next segment, it's made up of 2 of those 10 by 10 boxes, and so the center of mass of that piece would be halfway across, which is at x equals 10 centimeters, and it's halfway up, which is at y equals 25 centimeters. And so I can treat those 2 boxes as a single little point mass of mass 2m. And then this third piece, it's 3 boxes, so the mass is 3m, and it's halfway across, so this is 15 centimeters across, and it's halfway up, so it's halfway between 30 and 40, so it's at 35 centimeters on the y-axis. And so breaking it up into these 3 pieces, this ends up being just what we were doing for the other situations where you have 3 separate masses along an axis. You calculate the x, and here we also have y, but we're going to calculate the x and y coordinates of those 3 individual point masses. So first, calculate the x coordinate of the center of mass. We're going to do m1 x1 plus m2 x2 plus m3 x3 divided by the total mass of 8m plus 2m plus 3m. So m1, that's the 8m, its x coordinate is 20 centimeters. The second mass is 2m, its x coordinate is 10 centimeters, and the third mass is 3m, its x coordinate is 15 centimeters. So we have 8m times 20 centimeters plus 2m times 10 centimeters plus 3m times 15 centimeters divided by the total mass, 8 plus 2 plus 3m, so that's 13m. And so factoring an m out, we have m times 8 times 20 is 160, 2 times 10 is 20, 3 times 15 is 45. So we have m times 160 plus 20 plus 45 all over 13m. We can divide out those m's, and we have 225 over 13, which is 17.308 centimeters. So that's the x coordinate of the center of mass. We also need to find the y coordinate of the center of mass. The y coordinate of the center of mass will do the same way. So we take each mass times its y position. So we have this first object, which has a mass of 8m. It's at a height of 10 centimeters. We have this next object, which is 2m, at a height of 25 centimeters. And we have this third object with the mass of 3m at a height of 35 centimeters. And again, we're going to divide by the total mass of 13m. And so in the numerator, we have 235m divided by 13m, which gives us a y coordinate of the center of mass of 18.077 centimeters. And so this was a 2-dimensional object, and so we have an x and a y coordinate to the center of mass of this object. This second example is another one where we're going to have to use calculus to solve. So we have a uniform flat plate of metal that's cut in this triangular shape. And so it has a height of 2 meters on the left side, and it goes down to a height of 0 meters, and it is 5 meters long along the x-axis. And we're going to calculate the x-coordinate of the center of mass. We're only going to look at the x-coordinate. We could do the same method that we're doing here in the y direction as well, but for this, we're just asked to calculate the x-coordinate of the center of mass. And so this is something where we have mass spread out over a certain area. We have an area density, and the symbol that often gets used for this area density is the Greek letter sigma. It's a lowercase sigma. This is sometimes thought of as a surface area density, which is why we use the Greek letter S, sigma. And so that surface area density is the total mass divided by the total area. Again, linear density is mass per length. Area density is mass per area. Volume density is mass per volume. So this area density is the mass divided by the area. And because it's uniform, it's just the total mass divided by the total area. And so to calculate this x-coordinate of the center of mass, we have to break this up into these strips. Each one is at a different value of x. This is similar to what we were doing in the previous video when we were finding the center of mass of the rod. Except here we're breaking up into these strips, and this strip has a width and a height to it. And so we break it up into this little tiny strip. The height of it is y, the width of it is dx, and that strip is located a distance x from the left end of the plate. That's where we're saying that x equals 0. So the mass of that little tiny strip, dm, again, dm stands for the infinitesimally small mass. It's the mass per area, that's area density, times the area of this little strip. But the area of this little strip is the height y times the width dx. That's that little area dA. So dm is sigma dA, or dm is sigma times the height y times dx. But the thing is, as x changes, y also changes. We need to come up with the relationship between y and x. And we get that by looking at this line. We know the equation of a line, y equals mx plus b. So y equals the slope. The slope of this line is negative 2/5. So it's the slope negative 2/5 times x plus the y-intercept, which is 2. So this gives us the relationship between y and x for any point along this line. So using that relationship, we can get an expression for dm that's just in terms of x. So dm was sigma, the mass per area, times the area, but the area is y times dx. Y is negative 2/5 x plus 2 times dx. And so substituting this in, we have this expression for dm in terms of x. And so for an object where we have a continuous mass distribution, the x-coordinate of the center of mass is given by 1 over the total mass times the integral of x dm. But again, we need x and dm. We need the variables to be the same, so we need to write dm in terms of x, which is what we were doing here, where dm was sigma times y, negative 2/5 x plus 2, times dx. And so substituting in, we have x times dm, sigma times negative 2/5 x plus 2 times dx. And this integral goes from the left end of the rod, x equals 0, to the right end of the rod, x equals 5. So it's 1 over m total times the integral from 0 to 5 of x times sigma times the quantity negative 2/5 x plus 2 times dx. And sigma, the area density, was the total mass divided by the total area. So if I substitute that in, I have mass over area, and then I am dividing by mass out front, so the masses divide out. So I have 1 over the area times this integral. So that gives 1 over the total area times the integral from 0 to 5 of the quantity negative 2/5 x squared plus 2x times dx. Again, I distributed the x through and substituted in for sigma. So integrating that, we have 1 over the area, and the integral of negative 2/5 x squared is negative 2/5 x cubed over 3, and the integral of 2x is 2 times x squared over 2, or just x squared, and we're going to evaluate that from x equals 0 to x equals 5. So substituting in those limits, we have 1 over the area. Substituting in x equals 5, we have negative 2/5 times 5 cubed over 3, so that's negative 50/3, plus 5 squared, 25, so that quantity, minus, plugging in 0, we have 0 plus 0. And so to fully solve this, we need to get rid of this area out of the equation. The area, it's just the area of a triangle. It has a height 2 and a width 5. So the area of a triangle is 1/2 the base times the height, 1/2 times 2 times 5. So the area of that triangle is 5. So substituting that in, we have 1/5, 1 over the area, times negative 50/3 plus 25. And so simplifying that out, we get that the x coordinate is 1.667 meters. Again, this same thing could be done looking at things along the y-axis. To do that, you would break it up into strips, but they would be horizontal strips. And so the thickness of the strip would be dy, the length of the strip would be x, so the area would be x times dy. We would still use this same equation, but instead of writing y in terms of x, we would need to solve for x in terms of y, and we would set it up and we would do something very similar. Again, to check to see if our answer makes sense, if this was a rectangular piece, the center of mass would have been at the halfway point, 2.5 meters. Because it's cut off, there's more mass that's on the left-hand side of it, and so our center of mass needs to be closer to this left end than it is the right end, and our final answer of 1.667 meters is over here closer to this left side. So in these situations where you have a continuous mass distribution, you're going to use this integral form of the center of mass equation. The x coordinate of the center of mass is 1 over m total times the integral of x dm. The y coordinate of the center of mass is 1 over m total times the integral of y dm. You could have the same thing with the z coordinate as well. But the biggest thing that you have to do is you have to be able to write dm in terms of your variable x or y. You have to get everything into one variable so that you're able to do the integral.